All right. So welcome back to another episode of Pollys Introduction of Computer Networks. So the new announcement today is just that Poly realized that there's a chance we might be able to continue with the lectures and solve quiz 17 and 18 this week. Okay, there's a chance. Okay, let's hope so. All right. If we get to solve 17 and 18 in the class, then these quizzes will also be due by Saturday, 6 p.m. All right. Good. Let's now check out the topics for today. So good news, we'll start Transport Layer Chapter 3. Okay, so in this video, you'll see an overview of the whole chapter, but mostly Polly telling what are the major functionalities the transport layer is doing, okay, and how it's done. Okay, and we'll be also introducing this thing called segment. That is how a packet is called in transport layer. You know what? Polly is just happy that we're starting chapter 3. The transport layer. We were at the application layer that's actually higher up. Transport layer, we're getting closer to the heart of the internet. So in the transport layer service, there are a number of important functionalities. Multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. Now each of these are important, but multiplexing, demultiplexing, flow control, these two are super simple. They'll be done in like one slide or a couple slides. Now, what's going to take us quite amount of time is this. Reliable data transfer. And then slightly less, congestion control. All right. And both of these functions are implemented in TCP. Reliable transport, congestion control. Now then you can imagine UDP being very simple. Right? It's a connectionless transport layer service versus TCP being connection oriented. So in UDP, you don't need to set up something ahead of time before we send data. But TCP, you need to have a setup process before we begin to send data packets. 3.1 is the overview section. So what I need to say here is this. The transport layer services is actually providing a logical communication channel between the two processes that are running on different end systems. All right. So there's a sender side of the process, sender side of the transport layer protocol, and there's also the receiver side of the transport layer protocol. And the functions is often corresponding each other. Sender side will take messages from the application layer and break it into a number of these smaller segments. And these segments will be passed down further to the network layer. Receiver side is going to take segments from the network layer, reassemble them back to the original message, and that message gets passed up to the application layer. That's when, if this guy here sends an HTTP request, this guy over here receives the HTTP request. So the web server here can begin parsing the HTTP request and then find out what is the object being requested, right? So this is the very basic function of the transport layer protocols. Take messages from application, break it into segments, reassemble segments into message, and pass it back up to the application layer receiver. Now, that breaking of the segments, passing of the segments, and reassembling of the segments are implemented in two different flavors, TCP versus UDP. One is reliable, the other is not. All right, so that's the major functionalities of the transport layers: multiplexing, demultiplexing, reliable data transfer. Flow control, very straightforward, but congestion control is also major. But not all the transport layer protocols implement all these functions. Okay, you'll hear later. Okay, and you see, transport layer is taking messages from higher layer, break them into segments, and then pass it down to the down to the network layer. Okay, so next video is to tell you a little bit more about the differences between the transport layer and the network layer. Transport layer versus network layer services. So transport layer there works closely with the application layer. It works also closely with the network layer. But we have not yet talked about network layer functionalities much. So let me just break it to you. What is the main role of these network layer protocols? So what they do is to provide communication between hosts. So meaning enabling sending of messages, sending of packets, or sending of segments through the internet and reaching the other host, the destination. from source host to destination host. Okay, so that is the purpose of network layer protocols. Transport layer, however, is just to establish a logical communication between processes. All right? So between two hosts, there are often multiple processes running. So transport layer handles a pair of processes at a time. So a pair of processes, and network layer handles a pair of hosts. The granularity, okay, of the channel, the entities of the channel are very different. Okay? So transport layer here rely on underlying network layer service. So if there's a process needing to send certain segments to another process, hey, how does the sending process know which way to pass it down further? Because internet is huge and in the middle. That is the network layer protocol's job. So logical connection between the sending transport layer and the receiving transport layer, that is kind of abstract. That's why I keep saying that it's a logical communication, because the network layer is going to handle and find a clear path between the two of them. All right. Now, let me try to use an analogy to explain so that it's more clear the distinction between a transport layer service to a network layer service. So the example is this. Anne here has 12 kids in the house, and Bill has also 12 kids in the house. Yeah, both big families. And for some reason, Anne's kids and Bill's kids are good friends to each other, right? So houses there, Anne's house and Bill's house, consider them as hosts. And each kid's generating letters sending to each other will be the processes. So 12 processes generating messages independently, okay, and trying to send them to Bill's houses and therefore reaching Bill's kids. So each letter generated by each kid is an application message. N and Bill will then be the transport layer service. So N here is the sending side of the transport layer service, taking all the envelopes and then drop it into the mailbox. So it's mixing all the envelopes into the mailbox. Bill, on the other hand, will take all the letters out of the mailbox and distribute each envelope to the destination processes, to each of the kids, right? So Bill there is demultiplexing the envelopes from the mailbox, and N there is multiplexing, okay, the envelopes into the mailbox. Now, the mailman, okay, taking all these envelopes from N's box and then go all the way to Bill's mailbox is the network layer protocol. All right, so mailman is the real person there needing to find a way and driving all the way to send all these messages. All right, so you see the transport layer, N and Bill. One is mixing all the messages and send it out. The other is taking the mixed message and then deliver further up to the rightful receivers. Okay. And next video is just to talk a little bit more about TCP and UDP. And there are two services again. TCP here does reliable transfer, but it actually does more. Packets are going to arrive in order. Packets, as they get sent, they will also be controlled. So sometimes you can send faster, but sometimes slower. And usually it's when there's congestion, then you send slower. If there's not congestion, TCP sender side will be sending more aggressively. There's also flow control, connection setup. Flow control is such that we do not overwhelm the receiver side buffer. Okay. Connection setup is, if you heard, TCP is a connection-oriented services as well. In order to provide these functionality, reliable transfer, in-order delivery, congestion control, and flow control, well, the sender and the receiver side of a TCP connection needs to, communicate a little bit more before setting up a connection. So that takes some time. So there's a connection setup process as well. UDP, on the other hand, is the complete opposite. It's not reliable. It does not guarantee order delivery. So UDP is essentially nothing versus TCP does a lot. So essentially at the transport layer, you have the two extreme of the services. Okay. So it's on top of the network layer, which is called the IP protocol, and it's best effort, meaning do nothing. All right, so no real extension of IP. And so UDP there is very simplistic. Take messages from application, break them into segments, pass it out. Receiver there, grab the segments from network layer, and then try to reassemble them back to the original message and pass it out to the application layer. Now, if there's any segment lost in the middle, that message gets passed up to the receiver side of the application layer protocol. It's not going to make too much sense, all right? Oh, and TCP UDP, one does reliable transfer congestion control, the other does nothing. None of them provide this delay guarantee, bandwidth guarantee, and none of them provide security guarantee. Okay, and you heard it earlier, the security is provided by this alternative service, but this alternative service is in fact implemented in the what? Application layer.
All right, so that was chapter 3.1. And now 3.2, which is to talk about the first functionality, okay, provided by the transport layer. So let me explain first what is multiplexing and what is demultiplexing.
3.6 multiplexing and demultiplexing. Well, if you still recall the end bill example, end kids sending to bill kids example, end is the multiplexer and bill there is the demultiplexer. Right? So if we focus on this example below, so this guy in the middle is a big server machine. There are multiple processes running. You see here, P1 is sending a message out. P2 is also sending a message out. Yeah, the transport layer and the server is doing this, multiplexing. So this host here, from P1 and P2's point of view, generating this message, okay, is the sender. Okay, so sender. So it handles data from multiple sockets or data from multiple processes. Add the transport layer header, so add a little bit more information on top of these packets. Okay. And so therefore later they can be used for the demuxing purpose. So when messages go out and reaching P3 and P4, and P3, P4 in return generates something back as it arrives back to the server and the transport layer. Yeah, transport layer of the server is going to be working as a multiplexer at the receiving side. And what it does is to look into the header, okay, in these packets and then decide whether it should be this socket, the message being forwarded to, or this other socket, the message being forwarded to, right? So very simplistic, but very important functionality.
All right, and it's time for the first quiz today. So this is quiz 16. All right, and let me move to my whiteboard mode. Yeah, quiz 16 here. So we have two devices, A and B. Okay, A side are these mailboxes. Okay, so this is Taiwanese postal system. When you do have letters that you want to send out, you throw those letters into these mailboxes. Okay, I think the green one are for the domestic letters, the letters where the destinations are within Taiwan. And these are for like international destinations, okay, the red box. On the other side, we can have people like the mail lady here trying to sort the letter out and then put the letter into the boxes belonging to the receiver of the letter. Okay, so you see, the postal system works very much like the internet. Okay, so Q1 asks here, between A and B, which one is the multiplexer and which one is the demultiplexer? Quite simple, isn't it? Q2 asks, this is a slightly more complicated. What's on the envelope that the mail lady here is checking so that it allows demultiplexing? Okay, now go to channel W8, quiz 16. Okay, you have 3 minutes to work on this quiz, and let's go. You know what? We have team 3, 4, and 10 here saying that the multiplexer is A, the mailbox. Demultiplexer being the postman or the mail lady, right? And the stuff on the envelope that the mail lady uses to differentiate which box to drop is exactly the address, okay, on the receiver side of the envelope. Okay, good. Oh, okay, team A is saying that the address, particularly the floor. Yeah, because hey, this mail lady looks like she is already in an apartment building, right? So there's probably a stack of letters that are all destined to this apartment building. But the mail lady still need to distribute the letters, although the street address are the same, but the floor or the apartment unit number might not be the same. You see that the street address is also hierarchical, right? You have city, you have district, you have the street name, and then sometimes you have sections or lanes, or in the end, there's a number, okay? The number on the street, the number on the lane. But then, at the very end, there's also the unit number, the floor number. All right, so I guess the mail lady will need to sort the envelopes out in the post office based on the exact street address first. And then when they arrive at the apartment building, they just pull out the stack belonging to the particular address. And then sort the envelopes, okay, by the unit number, by the floor number. Okay, good. Great, so you guys got it. Okay, it's the receivers, the destination address that's allowing the demultiplexer to demultiplex. And what you are seeing there is also that, hey, the mail lady, it's checking the receiver's address to decide which box to drop. Does she check the sender's address? It doesn't seem necessary, right? Because we kind of receive letters from everyone. In fact, the mail lady there does not care what the source is. And that is a kind of demultiplexing service called the connectionless demultiplexing. And that is what I'm going to talk about in this video. Connectionless demultiplexing.
And the first form of demultiplexing is called connectionless demultiplexing. And this is also the kind of demultiplexing being carried out by a UDP connection. All right. So in this type of demultiplexing, we rely only on the destination IP address and destination port number to decide which socket to pass a packet towards. So it's only a two-element tuple. Right? So when a host receives an UDP segment, it checks the destination port number in the segment and then direct the segment to the socket carrying that port number. And that's pretty much it. Now, of course, the IP address is important because the host at the network layer would be able to decide, whether this particular host is the destination of this packet, therefore keeping the packet and pass it up to the transport layer. And the transport layer could handle this. Yeah, receiving a UDP segment, check the port number, and so on and so forth. All right. So datagrams with different source IP address and different source port numbers, as long as they come to the same IP address, same destination port number, they will be going through the same socket. Okay, so demultiplexing for UDP is slightly simpler. All we care about is the destination address and port number. So here's an example of connectionless DMUX. So port 9157 is where P3 is sitting on. So that's one of the clients. Port 5775 is process P4 that is sitting on. So that's another client. Server in the middle, open up a port number 642A, and P1 there is the server processing. It's waiting for requests to come in. So we see here a service request message being generated from P3 and intended for P1. You will see source port number being 9157 and the destination port number being, the server's port number 642A. And the return messages, so replies from the server will then be carrying the source port number being the server's port number and the destination port number being the sender's port number, the original request sender's port number, 9157, the client's port number. So you see also a little bit that how P1 can generate the reply. The port numbers are essentially the reverse, okay, of the requests. Now, if there's another request coming from P4, what is going to be the source port number? Yep, 5775. And destination? Yeah, the server's port number. And it's probably not hard. Yeah, the returning messages back to P4, source being 642A, essentially the reverse, yeah, of these two port numbers.
All right, so that is the connectionless demultiplexing. So you can actually think of, keep in mind the analogy. The postal, the street address is pretty much like the destination IP address. But the unit number, okay, once we all arrive, once all the letters arrive in the building, okay, the port number will be the number to separate the processes, okay, to separate the letters into individual households, okay, good. Now, this is not the only demultiplexer there is. On the internet, there's another kind of demultiplexer. It's called the opposite connection-oriented demultiplexing. And this one, you guess, it checks not only the destination address, but also the source address.
The slightly more complicated one is the connection-oriented demux. That is also the TCP's demultiplexer. So whether a packet or a segment should go to a particular socket depends on O4 information. All right, so receiver uses O4 values to direct the segment to the socket. Now, a server process running there on the host could be maintaining multiple sockets, okay, for each pair of communication per client. So, for example, a web server, yeah, the web processes there could have multiple sockets open for each of the connecting client. And if this is older form of HTTP the web server is running, it could be one socket per object request. Now, let me use an example to illustrate and explain. So we have a scenario where we have three segments being sent from clients over here, A and C, to the server in the middle, B. So all three segments destined to B, and they're supposed to be demuxed into different sockets. Now, P4 sockets will be using a 4-tuple to decide. And what will be the 4-tuple? Well, source IP address, A, destination IP address, B, and what? Source port number and the destination port number. So these 4 values is going to be associated with this socket. So when there's a segment arriving at the transport layer, matching the 4-tuple, therefore going to the socket. Similarly, for each of the sockets here and there, the 4 tuples will be stored, and the transport layer looking at the packet header, when there's a match, pass it up to socket to the processes. So that's the idea behind connection-oriented demux. And the reason it's called a connection-oriented demux is because it's not only looking at the destination, it cares also who the sources is. So it's almost like there's a one connection between the source and destination already, okay, the socket. Now, this connection-oriented demux socket is a little bit weird. And this actually happens quite often these days when we're doing this threaded server. Okay, so in your PA4, you are implementing a server, all right. What happened there is that you are starting a listening socket, isn't it? Listening socket is a little bit special because no matter where the client is, whatever the source IP is, request coming in, it's gonna be passed to that server socket, that listening socket, all right, even though the 4-tuple does not quite match, especially the source IP address and the port number. Okay. This type of connection-oriented demux, it is TCP, all right, but it only looks at the destination port number and the destination IP address. Therefore, the message is coming out this way, source being A, source port number 9157. This one here, source being C, port number again different. But then they will all be accepted by the listening socket here.
All right, so let me emphasize. The IP address is a little bit more like the street address on the envelope. The port number is a little bit more like the apartment unit number on the envelope. Okay. And on the internet, we have connectionless demultiplexing and connection-oriented demultiplexing. In the postal system, we only have the connectionless demultiplexing. Okay, but nowadays, if you think about it, if you don't want spam mails that much, maybe the postal system can implement some sort of connection-oriented demultiplexing there, so that we can actually list what source addresses we refuse taking mails in. Okay, very interesting, isn't it? But I'm not quite sure that the postal systems are innovative like that as much as the internet. Now, let's move on to the next topic. UDP is one of the two services that we implement in the transport layer. And this service implements exactly just the multiplexing and demultiplexing functionality.
UDP stands for User Datagram Protocol. As we've discussed many times, UDP does pretty much nothing on top of the network layer basic service. So we could have segment lost, we could have segments arriving out of order. So no reliability, unreliable. Second characteristic of UDP is this: it's connectionless. Therefore, there's no handshaking, there's no connection setup phase, there's no connection setup delay. As soon as we have data to send, we just generate these UDP segments and push it out. Very low delay. While we have also very low reliability. Right. But hey, some applications would actually like low delay, and it probably doesn't care too much about reliability, then these applications will be perfectly fine using UDP as a transport layer service. So some of the video streaming services, some of the gaming services that we talked about uses UDP. Skype's voice sometimes also uses UDP. DNS, getting the host to IP mapping, we need it as soon as possible. Therefore, UDP here. Now, if one of these DNS query or reply is lost, DNS server, the local DNS server is going to send another request real fast, so don't worry. And SNMP, okay, we have not yet talked about this protocol. It's called the Simple Network Management Protocol. Now, this protocol is talked about in the textbook, but it's in one of the later chapters. Most of the content there is to talk about building a database, defining the format, such that when we measure, for example, round-trip delay from one host to another host, we get to store these round-trip delay data. We get to store packet loss rate data. We get to store available bandwidth measurement data. Right? So SNMP there define these data structure for informations that measures the performance of the internet. SNMP also gets set up across all the machines around the world. If they are enabled, these machines will send these SNMP messages back to the SNMP database. And those messages are sent using UDP, because after all, these informations are nice to have, but they are not really necessary there to ensure the internet continues to operate. It tries to help such that the internet can perform a little bit better. But without these messages, the internet usually works just fine. Right? So those messages are also in UDP. Last point here. UDP does not do reliable transfer, but some applications might need reliable transfer services, but not 100% reliability is required. Then those might add the reliability at the level the application desires, okay, and does application-specific error recovery. So this is one of the reasons people use UDP. Not only because some applications doesn't care about having segment loss, some applications wishes the messages being really fast, and some applications want some level of reliability but not perfect reliability. There's some other use of UDP. Right? So some other advantages of UDP. There's no connection establishment, as we know, low delay. It's very simple. There's no handshake. It's easier to implement. There's also a small header. So this is a UDP segment. Once again, there's a header part. There's also a data part. The header part, very small, just 230 bits, 64 bits altogether, and that is a byte. Very small header. There's no congestion control, so you can actually blast into the internet as fast as possible. All right. So these are a few other advantages of people using UDP. Okay. So there are 4 fields in the header. The source and the destination port number, which we've already talked about. The 2 other fields we have not yet talked about is length. This is the size of the UDP segment entirely, including header and data. And the unit to count the length is byte. Last is the checksum. What's interesting about UDP is that, hey, if you send it out over UDP, there's no guaranteeing of reliable transfer, but you do get this. You get to check whether there's any bit errors in the data part of the UDP packet. And this is the way it works. It's called the UDP checksum.
All right, before I show you the video explaining the checksum, so you see UDP, very simple, okay, doesn't have fancy functionalities, but it's still useful, right? It's low delay, no connection establishment, it's very simple, okay. There's low packet header overhead, okay. It's very efficient in terms of transmitting the data bits. So DNS, SNMP, in fact, there'll be more protocols we'll be introducing later on in the network layer that uses also UDP. Okay. So now, finally, the video explaining how checksum works.
This is how it works. At the center side, we take the segment out. Okay, so take the entire segment, including the header, and lay the bits 1 row at a time, and each row 16 bits. So it looks a little bit more like this. Yeah, a row of 16 bits, another row of 16 bits. Okay, so you lay them out and then do what? Summing, okay, of these 16-bit rows. So add them up, and to be precise, it's called the ones complement sum, to be exact. Okay. And as a result, you get also a 16-bit output. That is called the UDP checksum. Right? So let's come back here in the example to explain how exactly it's done. So sum, binary add, 0 plus 1 writes 1 here, 1 plus 0 writes 1 here, 1 plus 1 writes 0 here, and carry 1 over here. That's why, even though these 2 are zeros, we still get 1 down here. Okay, just do the binary addition all the way till the end. Now, there could be extra bits being introduced. No worry, what we do in the ones complement sum is to wrap this around and then add back to the number here. So that 1 being added here writes 0, carry 1 over, writes 0, carry 1 over, writes 1 here, and that's the end. All right. Now the last thing is just to do what? To the complement. All right. So complement is straightforward, flipping 0 to 1 and flipping 1 to 0. And so in the end, we ended up having the checksum, which is also 16 bits. And this is what's being placed in this part of the UDP segment. All right. So when that UDP segment arrives at the receiver side, receiver does the exact computation, take the segment out, and compute the checksum. That checksum after computation is compared to the checksum field in the packet header. Right? If there's no bit error at all, right, the 2 checksums should match, isn't it? So if this equals this, if yes, then there should not be error. But now be careful. There could be specific bit error patterns that the checksum might not detect. Okay, so maybe error, but chances very low. All right. But otherwise, if the checksum do not match, so there's clearly some error. Okay, so application layer there, finding a UDP segment having mismatching checksum can at least discard the packet, discard the segment, knowing that there's already something wrong.
All right, so that was UDP. Okay, very straightforward. Starting from now, this is yet another subchapter, chapter 3.4. This is a chapter in transport layer that is the hardest to swallow. Okay, so guys, if you are not quite yet awake before this point, it's okay, but from this point and on, wake up. So this first set of video is to introduce the notations that we'll be using. So when Polly talks about the RDT, R there stands for reliable, D stands for data, and T stands for transfer. So RDT is exactly the name of the subchapter 3.4. Okay, so the notation there will look a little bit more like pseudocode. Okay, because chances very high that we will be talking about application layer passing a message down to the transport layer. And then the transport layer would do something, take actions. Okay, so pseudocode is what? Describing what in a program the actions are. So some of these actions could be straightforward, do something. Some of these actions could be like if condition, checking. If this is true, then do this. Otherwise, do that. And some of these actions can also be like a for loop. So you see that the application layer process, transport layer process, and network layer process, they might be passing something in between. Okay, and this passing is done by calling some functions, and these functions will also appear like pseudocodes. Okay, so now listen now to the first video introducing these pseudocode-like function calls.
All right, 3.4, principles of reliable data transfer. Now, you might see Polly is a little bit more alert talking about this section because this is going to be the most challenging section in chapter 3. And arguably, one of the most challenging section for the entire textbook. All right, so let's talk about reliable data transfer. It's not only challenging, it's also extremely important. All right. So it's not only important at the transport layer, some of the link layer services might also implement some level of reliable data transfer. At the application layer, someone might be using UDP as the underlying transport layer service and implement its own reliable data transfer. So maybe it'll be more efficient than TCP instead of using the native TCP provided in the protocol stack. All right. So it's one of the top problems when one needs to design a communication network. Now this is the setting. We have processes sitting at the application layer. Okay. There's application layer protocol, but there's also transport layer services. These processes depend down to transfer application level messages. So sending processes here, sending out data. Data will go through a channel. Now this is a reliable data transfer service, so the channel is reliable. And hopefully, at the other end, the receiving process grabs the data and then interpret the data and things will just work out. Okay. But the thing is, the internet is not exactly reliable, isn't it? So, yeah. We do have unreliable channel when packet goes through the internet infrastructure. Now, but application, sending process, receiving process are demanding reliable transfer. So transport layer service here. The sending side and the receiving side each will need to implement some extra mechanism to ensure somehow lost segment is recovered, somehow the flipped bits are corrected. Right? So that is RDT. Okay, and we're going to go through a few generations of these RDTs and show you how the sending side is implemented, how the receiving sides can be implemented such that we provide such a illusion to the application level services. Oh, and by the way, it really depends on how unreliable the channel is underlying. Then the complexity of the reliable data transfer can vary. Very unreliable, very complicated. Not that unreliable, then slightly simpler. Now, we'll be using these notations, RDT send, UDT send, and all these throughout the discussion, introducing you generations of these reliable data transfer protocols. So let me blow it up and explain a little bit further. All right, so sending processes here, generating messages. Those messages get passed down to the transport layer, and those messages are now called data. All right, and RDT send is the function called the sending process calls to pass the data down. Okay, so let me bring it up. RDT send here is to be called from above, from the sending process. Okay, and it is to pass the data down such that it will arrive at the receiver end. Good. Well, and these messages is going to be processed here, and a number of these segments will be generated, or packets will be generated. So when we're talking about generally reliable data protocol design, let's just call these packets. Okay, so messages now data, segments is now packet. And the action of pushing the packets down to the unreliable channel is UDT send. Okay, UDT send. So UDT send here is called by the RDT, the protocol sending side, to transfer packets over the unreliable channel. All right. And then, yeah, data is going to travel through the channel and come to the network layer. So that network layer component would call this, okay, RDT receive to pass the packet further up. So packets gets passed down by calling UDT send. Packets gets passed up, okay, by calling RDT receive. Okay, and this is called from below from the network layer when packet arrives. And those packets will be processed here, okay, and then the receiver side of the transport layer protocol is going to call yet another one, receiver data function. So this is called by RDT, the receiver side, to deliver data to the receiving process above. So data here is going to be passed above. So 4 function calls to refer to actions. First, coming from the sending process to the sending RDT. Second, from the sending RDT to the unreliable channel. Third, from the network layer to the receiving RDT. And the fourth, from the receiving RDT back up to the receiving process.
All right, so you see that pseudocode style function calls to indicate the actions between layers. Next video, it's a little bit long because you see that on the internet, we have sender receiver. So essentially you have 2 units there interacting with each other. And each of these units runs a particular process. Okay? The sending side and the receiving side might not be doing the same thing. So we need a set of variables to indicate the state of the sender as well as the state of the receiver. We also need to have the pseudocode describing the processes within each of the units. Okay, and so in order to do that, okay, and in order to communicate, okay, these things in concrete way and in a technically robust way, we introduce this thing next, the finite state machine. Okay.
Now, we'll try to describe generations of these reliable data transfer protocols. As Polly mentioned slightly earlier, yeah, these various generations, one is simpler, second slightly more complicated, third even more complicated. So they go from simpler RDTs to more complicated RDT. That's because we assume the underlying channel being more reliable to less reliable, to very, very general like the internet. All right. So that is just to prepare you for the RDTs that we need to introduce coming ahead. Now, another thing that I need to introduce is how I'm going to describe these RDT mechanisms. We're going to use, this thing called the finite state machines. Okay. Finite state machines, FSM. Okay, so here's one state, here's another state, 2 states. So finite number of states. All right, so this is a machine to go from one state to another station, from one state to another state. You might have a transition saying that under this condition, then we go from state 1 to state 2. And in the meantime, we transit from one state to another, we take this action. Right? So the arc here defines when will a machine jump from one state to another, and what is the action to be taken corresponding to this event occurring. Right? So at each state, there could be number of events, okay, that could trigger the state changes. And that could also trigger additional actions to be taken. Okay? So provided a machine, a mechanism, usually engineers can describe the mechanism using a finite state machine like this. All right. So FSM is also, if you recall, formal method, finite automata. When you're taking these courses, finite state machine is a notation that you should be familiar with because it's a way to describe a computational machine. Okay? And it's to describe it in a more formal way. Provided the machine, then the implementation will be straightforward. It's a little bit like when you take an algorithm course. After you learn how to write a pseudocode correctly, provided the pseudocode, your programmer that you hire will be able to program. Okay? That is the only thing that's required to communicate to the programmers. Oh, there's one more thing I neglected to mention. Yes, we only consider a unidirectional data transfer. So what I meant there is that one machine to another machine, data is going one way and there's no data coming back. Okay, so data go, receiver, okay, and receiver might send feedback back. Those are called the control info. Okay, control info can go both ways, but data only go from the sender to the receiver.
All right, so you see we use this finite state machine to describe the process on the sender side and the finite state machine to describe the process at the receiver side. And you will see that these two finite machines will interact to some degree. So next video is to talk about the first version of RDT, which is also trivial, okay, assuming no error at all.
And now RDT 1.0, the generation number 1. Right? So in this generation, yeah, the assumption is very strong. We're simply assuming that the underlying channel is reliable. As a result, sending side of RDT, receiving side of RDT, there's nothing really needs to be done. So the machine is very simple. So this RDT 1.0 is just so that you are more familiar with the finite state machine notation, right? So underlying channel is perfect. No bit error, no lost packets. Okay, so the sender side of the finite state machine, FSM, will look just like this. Okay, so there is always at least one state that is also the starting state. There's no ending state for these machines because they'll be looping forever. Okay, so starting state is wait for call from above. Okay, so application calling data to be sent to the transport layer. So yeah, calling from application from the sending process is RDT send, isn't it? So when you run into this event, the sender there, yeah, will generate packet out of data. So data is the thing coming from the application, and packet is generated to be pushed down. And to push down, we call UDT send, right? So this is the FSM at the sender side. Similarly, at the receiver side, call from below. Right, so when that is happening, yeah, RDT receive being called, receiver side of the RDT 1.0 will just extract data out of the packet and deliver the data up to the application layer. All right, so again, events triggering changing of state, and the arc direction indicates which state it changes to. And so a loop coming back is saying that, hey, we stay at the same state. Right? In the meantime, we take these actions. So event triggering the transition. In the meantime, we make the transition take these actions. So you see, sender side keep being triggered from the application, calling this and triggering actions to occur, triggering the state being changed. So that is the general idea of FSM and using it to denote a functioning machine. All right. Sender sends data into the underlying channel. Yeah, here. Receiver sends data from underlying channel. Yeah, here. All right.
All right, so that's RDT 1.0. And you see that in the sender side machine, the process of taking data from the application layer and put it into a packet that is called the make_pkt. So we introduced one more kind of function in a pseudocode fashion to describe the whole process at the sender side of RDT 1.0. Similarly, at the receiver side, you see this extract function that is to describe the process of taking data out of the packet the receiver receives from the unreliable channel. Okay, good. Now, RDT 2.0. We have a little bit time here. You know what, guys? It's 11:09. It's probably not the best time to play the next video introducing the idea of RDT 2.0 because 1.0 is assuming no error. That's too idealistic. Let's relax that assumption and make the channel unreliable with bit errors. That's the spirit of RDT 2.0, what RDT 2.0 is trying to solve. But given the time, let's take a break now and let's come back at 11:19, okay, to start talking about RDT 2.0. So break. Okay, guys. Hey, we got good questions during the break. Walker was asking how come this RDT receive function and UDT send function, they are bidirectional. Because I think in the videos, I tried to set up the notation and the finite state machine. I said that, hey, the communication is unidirectional. But what I meant by that is the data is only sent from the sender to the receiver. And the receiver is not sending data to the sender. And that's all. Okay. RDT, RCV, and UDT send, they are bidirectional because, hey, the network layer at the sender side might pass something up to the transport layer of the sender. It's coming from the receiver. But that thing is not data. That thing is some sort of control message called acknowledgement or negative acknowledgement. And you'll hear actually about that in RDT 2.0. Okay, good timing helping me set up the stage for RDT 2.0. And Minglun, your question is also good. So it's an opportunity for me to clarify the confusion. So on the internet, the transport layer, those connection-oriented DMARCs is implemented, checking all 4 tuples. Okay, and it's implemented this way. Okay, and we just call that type of socket a connection-oriented DMARCs socket. Okay. Of course, you can actually think of it another way, right? You could actually ask to check just the destination and just the source address and port number for and then add a attribute that is the DMARCs type. In case the DMARCs type is connection-oriented, then of course you just check the source address and port number, then it's deterministic. Okay, I think I can totally understand your logic, and that way you only check three attributes, right? It might be more efficient. That's another way of implementing it. Let me put it that way. Okay, good. Now, hey, RDT 2.0, aren't you guys can wait? Aren't you guys can wait for it, all right?
And then RDT 2.0. So this is when the channel is no longer perfect, but it's not so bad either. We do have some problem, but just this problem, having bit errors, meaning the packets, okay, if you look inside, some of the bits might be flipped. Therefore, it failed passing the checksum at the receiver. So the computed checksum and the packet header checksum somehow didn't match. Receiver then detect bit error. The question is, how do we recover from this error? Well, you know, if you're thinking how to do this in the computer in the transport layer, I'm sure that it's very hard. But if you think this, how do humans recover from errors during conversation? Say, if Polly was trying to describe finite state machine and it sounded really fuzzy to you, what would you do? There you go, right? You type up in the live chat and ask, hey, what do you mean transition? What do you mean changing from state to another state? What do you mean a certain event occur and triggering the changing of the state? It's not clear. And Polly then will try to explain again. Now you retransmit the packet again. So sure, if you abstract this exchange of feedback and data and retransmission, you see the general idea seems to be receiver upon detecting error, sending feedback to the sender, sender retransmit the packet again, and hopefully the second time it's clear, no longer fuzzy. That is the general idea of RDT 2.0. So to describe RDT 2.0 a bit more formally, those feedback you're providing to me, in the computer system, they'll be either in this form or this form. So acknowledgement there is a positive feedback. Negative acknowledgements, therefore, the negative feedback. Acknowledgements there or acts there are to explicitly telling the sender everything is all right. And next here is to tell the sender, something's wrong, and therefore the sender can retransmit the packet. Okay, so retransmit of the packet is triggered by the receiving of next. This is exactly what's defined in RDT 2.0. So let me stress, there's first, detecting error. Second, sending back of the feedback from the receiver. And then retransmission of packet coming from the sender. in case negative acknowledgement is received.
All right, so makes sense, simple, right? Let the receiver send some sort of feedback back to indicate okay or no, it's not okay. Then sender resend when it's not okay. Good. So now let's check out the finite state machine of the sender, and the receiver.
Now, what's a little bit harder is to go over RDT 2.0's finite state machine. All right. Now, try to be a bit patient here. Let's focus on the sender side of the FSM first. This time we do have two states. One is wait for call from above. Oh, okay, this one is familiar, right? So this is the initial state. The sender is waiting for the application process to send data down to the transport layer. Okay, so wait for call from above. And there's going to be a transition triggered by this event, RDT send, the application calling and having data to send. The sender here, transport layer, will then create packets from data. And this time, in order to detect error, we need to add the checksum. All right, so hey, this is very abstract, but you get the idea. When you're generating the packet, we do need the data from the application layer, but we also need to compute the checksum. All right, so when we generate the segment, make sure that the checksum is somewhere in the header. Very good. So send packet is finally generated. So this is the segment. And sending side of the transport layer service calls UDT send to send the segment out through the underlying channel, right? And that also take the sender from the wait for call from above state to the what? Wait for ACK or NAG state. Oh yeah, so after we send the data out, then we'll be waiting for feedback from the receiver. Good, makes sense. All right. Now, hey, here, what's coming back as feedback could be positive and negative. So therefore, you see two transitions possible, one over here and the other over here. So this is the negative feedback case, and this is the positive feedback case. Now, the easier one is if the feedback coming back is positive, right? So this is when the sender receive a message back from the network layer, so it needs to be triggered by call from below, RDT receive, the receive packet. And you check whether the receive packet is positive. So if both conditions true, then hey, do nothing. So this is empty set, do nothing, and then return to wait for call from above state. Meaning, hey, positive feedback, so move on with the lecture, for example, so to speak. Right? So hey, Polly can actually teach more next. But if the feedback is negative, so if some of you say, hey, wait, no, not clear. Can you do this again? Can you talk about it again? Well, in that case, okay, RDT receive called and the feedback is negative. What? Yeah, Polly resend the packet. So UDT send, the packet that's generated being sent already once will be, yeah, sent once again. Okay, so it's a retransmission. Now, what's a bit interesting is this. When we're at the wait for ACK/NAG state, when we receive a negative feedback, we actually come back here again to wait for feedback. So hopefully the next one is going to be acknowledgement, and therefore we can leave the waiting for feedback state. Right? So that was sender side of RDT 2.0, the finite state machine. Now let's move to the receiver side. All right. Whew, there's only one state, cool. But there are two different transitions, one above, the other below. So they are both triggered by RDT receive. So receiver there would be, call from below from the network layer saying that network layer, I'm here and I got the segment for you. I got a datagram for you. All right. And then you grab the datagram, remove the IP header, and you see the segment. You try to do the checksum computation, isn't it? Right? And there are two different conditions. One is if the packet does have bit error, meaning the packet is corrupted. Then you need to do what? Send the negative feedback. So UDT send. So UDT send is what? To send the data down to the network layer. And so receiver there sending the data down to the network layer. Network layer is going to send it back to the sender. So UDT send NAC is the action being triggered. And receiver comes back to wait for call from below. So it could be a correct data packet. It could be an incorrect data packet, depending on which is the case. So incorrect calls this arc. Correct calls this arc. If it's not corrupted, extract the packet. okay, extract the data out of the packet, deliver the data up to the receiving process, okay, and then send back positive acknowledgement. All right. So sending feedback. But if everything is correct, the receiving part of the transport layer, receiving part of RDT 2.0 is yet to extract data and pass it further up to the application layer.
All right, so that's RDT 2.0's finite state machine. I hope it's not exactly complicated yet. Okay, but hey, that's get ourselves familiar with all these notations that we're using through two examples. Okay, sending data over RDT 2.0.
Okay, now let's walk through a couple examples to show you how the sending side and the receiving side of RDT interacts. Okay, so this is RDT 2.0. And this is an example showing that, hey, there's no bit error in the packets. So, originally, okay, the sender starts from the initial state, wait for call from above. Receiver here also, yeah, starting here, wait for call from below. All right, so now we get a call from above. Okay, RDT send being called from the application layer, the sending process. Now, sender side would actually take the data, add the checksum, and create a packet, send packet, and then call the UDT send to send it out. All right, so go through that, and that packet is going to arrive at the receiver end. Receiver side of RDT 2.0 will be called. Okay, but there's no error. Okay, so this is the no error case, so it's going to pass this condition, receiving a packet from below and it's not corrupted, therefore triggering these actions being taken. Data extracted out of the receive packet, delivered to the receiving process, and send back in positive acknowledgement. So let me remove the notes. Yeah, so we'll be triggering this transition and all these actions, and that message is going to come back here. Okay, so you see it flashes, but essentially we were waiting here, right? And that packet, egg packet, is true. Therefore, both together is true, and we do nothing and simply return to wait for a call from above. So this is the case between the interactions of the sender, RDT 2.0, and the receiver, RDT 2.0. Okay, let's do it again. Oops. Okay. At the beginning, here, starting state, here. Sender gets called from above, triggering these actions, taking a transition, and message is going to reach receiver here. Okay, and it matches this condition. Therefore, these are going to be triggered, and we stay in the wait for call from below state. And this is going to generate a message being sent back this way. Yeah, and because it's an ACK, therefore we trigger this transition, and the sender goes back to wait for call from above state. All right, so this is the no error example. The next example is more interesting, where there's error. All right, so similarly, sender starting from wait for call from above state, receiver starts from the wait for call from below state. And yeah, there's a call coming in. Okay, generating the packet, send the packet out through the network layer. Straightforward. So this event match and these actions taken, and we take the transition and move to the wait for ACK or NACK state. And that's going to generate a packet to the receiver. And this time, yeah, this event is triggered. Network layer says, I have a packet for you. And which of the condition matches? Well, we have error here this time, so it's corrupt. Therefore, we trigger this transition to occur. Condition match and this action, and then stay in the same state. So we'll be calling UDT send, and we are sending a negative feedback, the NACK. That's going to fly back. So sender here waiting in the ACK, waiting for ACK or NACK state, then gets a call from below. And it's checking and finds that it's a NACK, not the ACK. Therefore, this transition matches and being triggered. This action is being taken. So UDT send packet is what? Retransmission of the send packet generated earlier. Okay, and sender here stay in the wait for ACK or NACK state. So this is taken and packets being sent again. But the second time, Yeah, we're lucky. Second time it's not corrupted, therefore we trigger this transition and another packet being sent back. And this transition now, because of the condition being matching, yeah, we do nothing and we return. The sender returns to wait for call from above state. All right, should we do it again? Oh, probably not, right? You get the idea. Okay, so the interaction between the sending and the receiving machines of RDT 2.0, how they interact. Okay, so there are actions being triggered, and in the meantime, packets being generated, and they would go to the other end, and feedback being generated, coming back to the other end.
All right, so that was 2.0. It's a little bit more realistic, but it's not yet perfectly realistic. Some of you might be asking, hey, we actually consider bit errors at the data direction. What if the acknowledgement or negative acknowledgements have bit errors? That is exactly what RDT 2.1 is trying to address.
But RDT 2.0 has a fatal flaw. Yeah. If data can be corrupted, therefore a receiver needs to send ACK and NACK to provide feedback to the sender. The ACK and NACK coming from the receiver to the sender, those packets can also be corrupted. So what if that feedback packet is corrupted? Then sender will not know whether it's really an ACK or a NACK. So should the sender retransmit, or should the sender say, okay, I'm just gonna wait for another call from above? Dilemma. So what do we do with this? If you think a little bit further or recall back, didn't we have the same situation, right? So when data is corrupted, we ask the other end to send feedback. So perhaps we could ask the sender of the data to send feedback so that the receiver will know whether the ACK or NACK is corrupted, therefore retransmit the ACK or retransmit the NACK. Yeah. So how did we deal with the corrupted data? We do the checksum, right? And the receiver, well, actually, we do the checksum at the sender, adding that into the packet, and receiver check it again. Now, if it's not a match, we send NACK. If it's a match, we send ACK. So this is receiver side action. And therefore, at the sender side, we could retransmit data. So perhaps we will do this, right? So ACK, NACK corrupted. There's potential. So why don't we do checksum, okay, on the ACK, NACK? So receiver there adds checksum for the ACK, NACK. Sender there checks if the checksum matches. And sender, upon seeing a mismatch, sends a NACK for the ACK or NACK. If it's a match, sends an ACK for the ACK or NACK. Therefore, data receiver there can retransmit the ACK and NACK. Oh, makes sense. But if you think a little bit further, how do we ensure that the ACK NACK for the ACK NACK is going to arrive back at the receiver, right? What if these guys are corrupted and therefore the receiver will not be able to tell whether the former ACK NACK being sent is corrupted or not? Exactly. What happens if the ACK NACK of the ACK NACK gets corrupted? Okay, so you have circular dependency there, and the problem never gets solved. So alternative thinking coming next. The new thinking to address the circular dependency we saw earlier is this. The sender, okay, will just not figure it out, okay, whether it's ACK or NACK being corrupted, okay. So sender will just pretend to be dumb and not trying to ask for a clear answer. Sender here instead retransmit the data that's already sent to the receiver. Would that work? If the corrupted ACK NACK is a NACK, then hey, this addressed the issue, isn't it? If the corrupted feedback is an ACK, then this actually creates duplicates. So the receiver side, in case it being an ACK feedback being corrupted, might have duplicate data. So this is actually not good because at the receiver side, it's going to receive segments one after another, and it's just going to reassemble everything and then pass it up to the receiving process. If that's the case, you might see typos, duplicated sentences, duplicated phrases here, there in the document, or sometimes duplicated pictures or partial pictures. So in RDT 2.1, to really seriously addressing the issue, we need to add a sequence number to the packet sent so that the receiver side can check the sequence number and see if the packet that has already been received earlier matches the sequence number that I'm receiving now, the receiver is receiving now. If they match, then that is very likely a duplicate from the sender, okay? And the corrupted feedback is an ACK. So entirely in RDT 2.0, sender will just retransmit the current packet in case the feedback is corrupted. But in the packet, it's going to carry a sequence number that will allow the receiver to tell whether this is a duplicate or not. In case the receiver detects it's a duplicate, it would scar the duplicated packet. And this is RDT 2.1. And there's one more thing we need to talk about. That tells a little bit about the sequence number requirement here. Think a little bit more. RDT 2.0, RDT 2.1. The sender behaves this way. After sending one data packet, it's going to stop and wait for feedback until everything is cleared. Then it will go back to send data again. So sender sends one packet and it's going to wait for feedback until everything is cleared and move on. So you see, if the receiver during the phase in stop and wait state receiving two packets carrying the same sequence number, then that must be a duplicate due to a corrupted ACK, isn't it? Yeah, so sequence number in such form of reliable data transfer is very simple. It needs only one bit, two numbers, 0 and 1, to tell whether it's a duplicate apart from a new packet.
All right, so that is the mechanism of 2.1, but in description in English. So let's check out the finite state machine. Now you can probably appreciate finite state machines because then it will be concrete, okay, almost like pseudocode you follow. And now let's check out RDT 2.1 senders finite state machine.
Now, judging from the description, it sounded somewhat easy, not that complicated. But if we look at the finite state machine, it looks somewhat complicated. And you know what? This is only the sender side of the FSM. We have not yet looked at the receiver side, all right? So this is the sender side of RDT 2.1, which is the version of reliable data transfer that handles corrupted ACK coming back from the receiver. Now, the easiest way to look at the finite state machine here is by drawing a line separating the two mirror parts. So if you look at the upper right part of it, this looks like the wait for call from above state in RDT 2.0 sender, isn't it? And wait for ACK and NACK, this looks like the waiting for feedback state in RDT 2.0 sender. If you go down further, this other half, it's actually very similar. Wait for call from above, and then wait for ACK NACK. Okay, the only difference is this. Wait for call for packet 0 from above versus wait for call for packet 1 from above. We just talked about the sequence number required to separate two packets one after another from a duplicate, a retransmission of an existing packet, isn't it? So having 0 and 1 is a way to tell duplicate packet apart from a fresh packet. So we do need to have the separation here in RDT 2.1 sender. And as a result, when we get a call from above, so application calls RDT send data, will then trigger these actions to occur. So we'll be making packets, taking data, and we do the checksum, right? So this is in order for the receiver to check and see if the receiver sends ACK or NACK. The new thing we add here is to add sequence number to the packet we're creating. So the send packet here now contains not just data, not just checksum, but also a sequence number. And as usual, we send it out through the network layer. So we call at the transport layer called UDT send. Now, the second thing that is a bit unusual is also this. Hey, the feedback state, wait for feedback state, you see, wow, the condition looks all complicated. Particularly if you see, we're now checking first whether the feedback we receive is corrupted or not, whether it's actually intact or not. So this is the case when it's corrupted. This is the case when it's not corrupted. So if we receive a packet from the network layer, receive a feedback packet from the network layer, and we check that it's not corrupted, everything is fine. And that packet is a positive feedback. That means what? Transmission of packet 0, perfect. So we do nothing, and then we move on to wait for call from above again. All right, so this transition here is straightforward. Now, what is a little bit unstraightforward is this transition. So this is the transition that we come back to wait for feedback again. Okay, so these are the complicated cases. You see here, if the ACK or NAC coming back is corrupted, what do we do in RDT 2.1? We'll just retransmit the packet that's sent once earlier, isn't it? So if it's corrupted, simply send it again. So the send packet here is not actually being reassigned. So it will be the packet we have sent earlier. So it will be carrying sequence number 0. There's another condition. If the packet is not corrupted, but it is a negative acknowledgement, then it's just like in RDT 2.0, we retransmit. All right, so this transition here gets, doubled. It's checking two conditions. If it's not corrupted, a negative acknowledgement, retransmit. If it's corrupted, also retransmit. So we have two conditions that actually ended up doing the same thing, just retransmit. All right. And so that is the sender side of RDT 2.1, and we'll just not cover the rest of it because it's pretty much the mirror. Okay, the only difference is just that handling data packet 0 versus data packet 1.
And so you see here from the sender's finite state machine, what's new is to add that sequence number into the packet. And the check condition of whether we resend the data packet is a little bit more complicated. Now let's check out the receiver side of 2.1.
And this is the receiver of RDT 2.1. You see similarly the number of states and transitions also doubled. We borrow the technique I used to describe the sender side. So the line in the middle here actually indicates the upper left and the lower right. They are the mirror of each other. The difference is just that the upper left is handling data sequence number 0, expecting data sequence number 0. And the lower right expecting and handling sequence number 1. And then we propose that we walk through the state machine this way. First, assuming that there are not going to be any data corruptions nor the ACK/NAC corruptions, meaning things are going perfectly. At the beginning, receiver will start from the initial state, wait for packet 0 coming from below. And nothing's going to be wrong there, therefore it will be triggering, this condition, this transition. Okay, so receiving a packet, no corruption, and it's carrying sequence number 0 here. Okay, expecting 0, carrying sequence number 0, perfect. Let's extract the data, pass it up to the application layer, generate the ACK packet, but this time what? Including the checksum. So this is coded in RDT 2.1 because we are now assuming also ACK/NAC could be corrupted. So checksum here is to enable the data center to be able to check whether the ACK packet or the NAC packet is corrupted. So that ACK packet with the checksum will be generated and sent back. All right, straightforward. And we move to the new state, wait for 0 from below. Similarly, we'll be getting a packet from below, receive RDT, and not corrupted, and carrying the expected sequence number 1. Cool, happy again. Extract data out of the packet, pass it up to the application layer, generating an ACK with checksum, send it back. Upon finishing all these actions, we take the transition, receiver here, go back to wait for 0 from below. If another packet comes in, not corrupted, carrying sequence number 0, again happy, take the transition, wait for 1 below, and this will go on and on and on and on and on. And when there's no data corruption, when there's no ACK/NAC corruption. Now, what if there's data corruption in RDT 2.0? That's where we begin to see these transitions showing in the receiver side of RDT 2.0. This is the case when we are expecting 1, but we get the corrupted data. Then we say, hey, the data is corrupted. generate a negative acknowledgement, but hey, in RDT2.1, we do need to include the checksum and send it back to the data center. Similarly here, if we're expecting 0, receiving a packet, it's corrupted. Generate the neg, send it back to the data center. Okay, so these two transitions we know well. Okay, they have already appeared in RDT2.0. The two transitions remaining, yeah, this one and this one here. So this guy and this guy here. Okay. Just like these two, very similar. These two, very similar. They are actually very similar as well. So let's focus on this guy here. So this is the case when we are waiting for packet 0 to arrive. We did get a packet, it's not corrupted, but wrong sequence number. How can this be happening? Well, then this must be because, hey, sequence 1 here has already been received earlier. That's why we've already moved on to wait for 0. Now, receiver here, receiving 1, will be also sending an ACK back to the data center. But the data center there finds that packet corrupted. Okay, that's when the sender retransmit sequence 1, thinking, hey, I'm not sure, I'll just retransmit. And therefore, we get a duplicate packet here. All right, so if that's a duplicate, no, that's not extract packet, that's not deliver, again, the same thing out to the application layer. So you see here, the only actions we'll be taking is just not extracting data, not passing up to the application layer, but only to generate the acknowledgement and send it back to the sender. Now, is it necessary to generate another ACK? It is, isn't it? Because the previous ACK here, yeah, it was corrupted. So sender there is just gonna think that data might not be there. Data might not be there. To be safe, let's just retransmit. So this ACK here is actually crucial, so that the sender, hopefully the second time, gets the ACK all right and they can move on to what? Wait for call from above for packet 0, because it's now stuck at the packet 1's feedback. So yeah, this is RDT 2.1.
All right, so let's also check out a couple examples to exercise RDT 2.1.
Now let's use a couple very simple scenarios to demonstrate how the sender and the receiver interact. So this is our RDT 2.1, no error case, and scenario is simply first to send one packet, and then second, continue and send yet another packet. Okay. So our goal is to find out all the transitions being triggered until it reaches the steady state. Now, in order to find out what transitions each of these finite state machines will be taking, we need to know the starting state. Now, at the beginning of the sender, it's going to start from the initial state. So the starting state will be the initial state for the first transition. Similarly for the receiver, this is the initial state. Therefore, the starting state of the first transition at the receiver side is going to be also the initial state. Now, event is that send one packet. Now, we're here at the starting state to determine what transitions to take. Let's check out what the transitions are. Well, starting from this state, there's only one possibility, which is T1. And it happens to be what? Getting a call from above, which is to send one packet. So obviously, the first transition we'll be taking is at the sender side, and it's T1. And it matches this event here, and it's going to complete all the actions listed here, which is to generate data packet 0 and send it out. At this point, sender here enters the wait for ACK or NAG 0 state. Right? So very important, before you determine what transition to take next, what is the starting state right now? What are the possibilities? Are there multiple transitions one can take from the starting state? If there are, be careful. What is the triggering event? Okay, so pick the transition that's matching the triggering event. And then take the actions, and then finish the transition, and land on the ending state. All right, so let me repeat, starting state, possible transitions, match the triggering event, and then land on the ending state. So now we're done with T1. So the result of T1 is there's a packet being generated, isn't it? And that's going to arrive at the receiver side. Receiver side, currently here. So this is going to be the starting state of the next transition being triggered. And it's receiving a packet from below. So let's see, what are the possible transitions? 1, 2, 3, because all 3 of them starts from the state here. Now, event is, yeah, we receive a packet, definitely. Okay. So all transitions is triggered by receiving a packet. But exactly which one is triggered depends on checking whether the packet is corrupted or not. And we're assuming no error, so this one is not possible. So this one passed to this point, this one passed to this point. But there's one more check. Is the packet sequence number 0 or sequence number 1? Here, we are generating sequence number 0. Therefore, eventually this transition waits. And so we'll be taking T11 over here and taking all these actions and moving the receiver to this state. Wait for 1 from below. And now next, right over here, the receiver is generating an add packet and it's being sent back. So that's gonna trigger an add packet arriving back at the sender. So sender here currently at the wait for ACK or NAC 0 state. See, there are 2 possible transitions. So which of these matches the ACK packet with no error? Yeah, this one here. No error and it's ACK packet. So we'll be taking T2 and finish all the action here, which is doing nothing, and enter the wait for call 1 from above state. So sender here goes to the state. And there's nothing to be done here. No more packet being generated flying back to the receiver. So we could have stabilized this right here. So sender here, stop here. Receiver, stop here. Okay. And in the process, we take 3 transitions. First one is T1 at the sender side. Second is what? T11 at the receiver side. And the third being T2 at the sender side.
All right, good. Now, let me just emphasize one more thing. Okay, what you do there, again, 5 steps to check. From the starting state, you check what are the possible transitions and you match for one, provided the data or provided the packet you receive. Take the actions indicated by the transition and move to the ending state, and again, indicated by the transition. All right, so keep these 5 steps in mind, and that's try to exercise RDT 2.1 with quiz 17 and 18. Okay, so quiz 17 is saying this, RDT 2.1 with errors. Okay, so in the video you see scenario 1 is to send one data. Okay, and scenario 2 is essentially sending another data. All right, now scenario 3, send one data, but there's a bit error in the data. Okay, so scenario 1 and 2 both don't have errors. Now this is sending a data packet with error. Okay, so go to channel WA quiz 17. Okay, starting from the initial state. Okay, so wait, let me go back to the side here. Starting from the initial state here, wait for call 0 from above. Okay, send one packet, but there's a bit error. And then after that, there's no more bit errors. Okay, meaning whatever ACK/NAC generated by the receiver, there's no more error. Okay, and this just one packet to be sent. All right. So go to channel WA quiz 17 and you have 3 minutes to tell Polly what is the sequence of transitions that will be triggered until both the sender and receiver stabilize. 3 minutes. We'll see whether the time is sufficient. Okay, I guess I was right, right? So if you just, pretend that you are a finite state machine, you just follow exactly what's defined in the finite state machine. It's quite straightforward, right? So sender side triggers T1, send a packet. At the receiver side, because there's a bit error, so we trigger T15. Okay, that's the packet, that is the transition. We receive a packet from below, but the packet is corrupted. Right? So it's T15. Yeah, T15 is the transition that we receive a packet, and if the packet is corrupted, right? What do we do here? We generate NAC and send the NAC back to the sender. Okay, data sender will receive the packet, and it's gonna be a NAC, therefore triggering T5. Retransmission of the packet that has a bit error, and then finally T11 and T2. Okay, great. So not that hard, all right? But what about quiz 18? Okay, so this is to continue from scenario 3. So at this point, the sender is at what? Wait for call 1 from above. The receiver is at wait for what? Wait for 1 from below, I think. Okay, so the starting state of the machines are actually slightly different. Okay, and the condition is this: we send 1 more packet, but there's a bit error in the return NAC. Returned NAC. Okay, so yeah, we are here. Okay, sender here, receiver currently here. We send 1 more packet, and then there's a bit error in the return NAC. So that means this guy, receiver here, sends back a NAC, and there's a bit error in that NAC. Okay, so now go to channel W8, quiz 18. And tell Polly, what is the series of transitions, okay, that will be taken until both the sender and receiver stabilize? Okay, you have 5 minutes. Okay, it's just slightly more tricky. All right, yeah, so it turned out that 5 minutes is also about right, right? So you get it. T3, T13, T6, T12, and T4. I understand that this one might not be so obvious for all of you, so here's the animation. Okay, so here, sender starts here, receiver starts here. Sender sends a packet, so triggering T3. And sender will enter this state, wait for ACK or NACK for 1. That packet would arrive at the receiver. But you see, hey, receiver returned the NACK. So which transition? Okay, so receiver is here. Okay, there are 3 transitions. Which transition is triggered? Which transition ended up sending a NACK? Hey, T13, right? This guy here, T14 sends an ACK. T12 is actually sending an ACK as well. Okay, so T13 is the only possibility. Okay, great. So, wait a minute. Oh, okay, sorry. This is the wrong animation. Oopsie. Do I still have the neck animation? Ah, there. Okay. Yeah, so send the data. This is the only transition, T13, that can be triggered. Okay. And a NAG is generated and sent back. When the NAG arrives, sender is here, so T6 will be triggered, isn't it? Okay, because it's checking the condition. It's either corrupt or NAC, then T6 is triggered, and this is a NAC, so T6 triggered. Okay. As a result, we send this what? The send packet is pre-generated here. Okay, that is the same packet 1 we're generating, and it's going to come back to the receiver. There's no more error, so no more be errors afterwards. Therefore, okay, packet received, no corruption, and it's sequence 1 matching this transition. And so we'll take these actions. Receiver will move to the wait for 0 from below state. And this packet here, the ACK packet, will finally come back to the sender. Sender currently here having 1 and 2 options. Which one is triggered? It's received and it's not corrupted and it's an ACK. Therefore, we trigger T4. Okay, the action is empty set, so we do nothing, and in the meantime, move to the ending state. Okay, so this is a quiz 18 solution for S4. Okay, the bit error there's a bit error in the return NAC. Okay, and you know what? That is all the time we have. There's a short summary video, but we'll play that next Wednesday. So 2.1 is somewhat complete in terms of reliable data transfer. There was a question from a student. Well, actually, a suggestion from a student, K-Kist. I'm not sure who you are exactly, but when we were talking about designing RDT 2.1, the student mentioned using timer. Okay, so that is actually to address a condition. So far, what we have considered are just having bit errors in the packet. What if the packet don't arrive at the receiver at all? That's an error. But does RDT 2.1 handle that case? No. So RDT 2.1 is not the end of the story yet. Next week, we'll talk about RDT 2.2. 2.2, however, is actually isomorphic to 2.1. It's just a little bit more compact. The finite state machine and the data representation more compact. And then RDT 3.0 is the version to address the case of having packet loss. So today, we just talk about handling bit errors in a packet. Next week, we talk about the packet is lost, dropped entirely. Can that happen on the internet? Yeah, we do have routers, right? There are queues. When the queue is full, packet get dropped. They never come to the receiver. Okay, good. Keep that in mind, and that's all for this week. With that said, I say goodbye, and the goodbye music. Alright, so let me end the stream, and